Okay, so I'd like to thank you for choosing to come to this talk. My name is Chris Drom, and I'm an engineer on the Hive and HCatalog team at Yahoo. And today I'll be talking about some of the work that we've been doing to improve performance on the database layer in the Hive Metastore. So let's set the stage. We have 20 plus clusters that run Hive. Each cluster has 2 to 4 dedicated Metastore servers, and these are backed by Oracle racks, which are often shared with other clusters and or services. So a Metastore that's running on a large cluster for us typically has anywhere between 6 and 9 million partitions and roughly 6,000 tables that it manages. The largest table in one of these large clusters has over 1.1 million partitions registered. A medium cluster would have somewhere in the range of 3 to 6 million partitions and anywhere between 3 and, say, 4,000 tables. So anyone who manages Metastores in this sort of size range should recognize some of the issues and things that I'll be talking about in the context of this presentation. So imagine this situation, if you will. A user comes up to you and he says that he's having problems, he or she is having problems because their query is taking too long to start, or maybe the query isn't even starting at all because of client-side timeouts. So you look at the query and you notice that the query is attempting to access a large number of partitions. So your next step is to go onto the Metastore server itself, and you notice that there's an increased load and there's increased memory usage on this server. And you see that this user isn't the only one who's executing similar types of queries of this scope. Worse still, the Metastore seems to be getting multiple copies of the exact same request or operation request to perform an operation from the same client. So this typically happens because the client times out on a particular, waiting for the results for a particular operation, and it triggers an automatic retry attempt. Either that or the query failed to execute entirely, and the user launches a new instance of that particular query that he's running. So furthermore, when you dig in a little bit deeper, you notice that even though the client has timed out, there are still those operations that it had fired onto the Metastore, which are still running on the Metastore. So these abandoned requests are destined to continue running to completion. They'll generate a result set, and they'll have no one to send the result set to, because the client has timed out and severed its connection. So in effect, it's just wasting these resources on computing that result set. So now consider what's happening on the database side of things. We've also got an increased load that's happening on the Oracle side. And this is coming about because we've got multiple Metastores, which are multi-threaded. They're taking in requests from multiple users and launching relatively long-lived queries to try to retrieve information from the Metastore. So you can see that as you scale out the Metastore, you have this potential for quickly building up a large number of queries that you ideally want to run through very quickly on the Oracle side. Unfortunately, in this case that I'm illustrating, that's not happening, and we're actually seeing queries starting to back up on the Oracle side. And the unfortunate side effect of that is queries that used to run very well are now also being impacted by this. So I think you can see where this is heading, and it's not very pleasant. So let's introduce the actors here. So the Metastore is a thrift server which implements a thrift-based communication protocol between the clients and the server. Then there's some core logic which executes the user request, and it uses some code or classes called ObjectStore and DIRECTSOL to persist and retrieve objects from the underlying storage layer. The ObjectStore delegates this task to DATANUCLEUS, which is responsible for doing all operations against the database. So it uses a model that helps define a mapping between the in-memory objects that are inside the Java JVM, and it tells how those objects should be serialized into sort of storage in the relational database. So these are sort of the components that we're interested in talking about today. So what is DATANUCLEUS? So as I mentioned, it's an ORM framework that defines a mapping between the objects that exist in the JVM and their data representation in an RDBMS. It also generates database-specific SQL from a programmatic language called JDOQL. But what does all of this mean to us? In effect, it's just really a black box, and what that means is that it's often hard to tune, optimize, and debug when you have to. Furthermore, it introduces its own set of model objects, or ORM objects, that it uses to shift data back and forth between the database and the JVM. So that in turn requires some sort of a mechanism to convert those ORM objects into thrift objects, which are used in the core logic level or layer and the thrift communication layers. So the next item on this list is sort of a really big topic, and it's fundamental to all ORM frameworks. That's the object relational impedance mismatch. So it is a big topic to discuss. I'm not going to go into it here. You know, feel free if you're interested to look at what it is. But the important thing to take away from this is the understanding that any ORM layer has to set out a certain set of rules in how it's going to deal with taking objects that are in memory and converting those into some form that it will be able to store in a relational database. So this is basically the price of admission for using any type of ORM layer like we are in the Hive Metastore. And the final thing is, because the ORM layer is basically obfuscating or hiding the storage mechanism that underlies it, it's basically doing the same thing to the language that it uses to interact with that mechanism. So in our case, that means that it pretty much hides the SQL or the SQL from you. So there was another component that I mentioned in the architecture slide called DIRECTSOL. And what is that? So it's a set of code that was introduced into the Metastore to address one of the sort of fundamental failings of DATANUCLEUS, which caused serious performance issues. So it still works through the DATANUCLEUS framework, but it greatly improves the performance when retrieving lists of objects from the underlying data store. So it does this by executing batch queries, and it directly hits the underlying database. So in our case, that's Oracle. But again, what does that mean to us? It sort of means that it's an admission that DATANUCLEUS's implementation of this type of operation is really suboptimal and breaks down when you're dealing with large result sets. And because of how this code was implemented, in the fact that it sort of circumvents all of the parts of that make the ORM layer and directly hits the underlying database, it requires a bunch of code in order to be able to probe and figure out what that underlying database is and what flavor of SQL it's actually talking. So the third item here is referring to the implementation details of DirectSQL, where it implements a timer which is set any time that that code path is executed, and that's to prevent it from taking an overly long period of time to execute the user request. So in the case of any sort of failure or any timeout by this timer, the DirectSQL execution is going to fall back to the ORM level execution, which again, we've already talked about is suboptimal and inevitably is going to take a lot longer than the execution would have taken under DirectSQL. And this leads to further latencies. And the last point that I want to mention here is that because DirectSQL is still working within the framework of DATANUCLEUS, it can't really address some of the other fundamental issues that we'll be talking about in this presentation. So I think it's a really good approach to fixing some of the deficiencies in DATANUCLEUS itself, but there's a lot of room for improvement on top of that. So we've set the stage and we've introduced the actors, but what are we really trying to achieve here? So ultimately, what we want to do is reduce the load on the underlying database by running more efficient queries on a more efficient schema. We also want to introduce we also want to address as future work the problem of repeatedly answering requests from the same client for the exact same data. So I'll come back and touch upon this point later on in the presentation. And this typically happens during the query planning phase. And the last point here is that a lot of the techniques and strategies that we apply to increasing the performance of the database layer can be applied to optimizing the communications, the Thrift communications layer as well. So there's a lot of commonality that we should be able to leverage from what we're doing here. And that should ultimately result in a much smaller payload being sent back to the client. So this all sounds well and good, hopefully, but how are we going to get there? So the first thing, as with any good self-help program, is to admit that there is a problem. Then what we're going to have to do is look at the existing schema and identify what the pain points are for that schema, and conversely, the opportunities we have for being able to optimize certain parts of the schema. So once we've itemized these, we have to also think about how the original schema design decisions impact the query performance on that schema. So once we gather this information, we can go forward and design a hopefully much more performant schema to back our OracleStore implementation. Then we'd write some code, which we're calling OracleStore, that would in effect replace the code that we're using, the code that we pull in via the database, the DATANUCLEUS dependencies. So finally, before we are able to take all of this new code, new schemas and whatnot, and actually deploy it, we need two other things before we can actually deploy it. The first thing is we'll need some mechanism to take data that's in the existing schema and migrate it into the new schema. The other thing that we'll need is once the data has been migrated and once we start ingesting new data, we'll need some sort of a mechanism to validate the integrity of the data, hopefully comparing it against the data that was in the original schema. So that's our plan. Now, when we went and looked at the existing schema, what were the things that we took away? What did we learn from it? Possibly the most important thing that we learned was that the structure and the relationship of the in-memory objects should not impact or should not be allowed to dictate the underlying schema that we use in the database. So second, operations that are performed on table objects are the most frequently executed operations in the Metastore. And operations that are performed on partition objects are the most expensive. So we should keep that in mind when we're designing the schema, and we should arrange things accordingly so that we can further optimize operations on those types of objects. And the last thing that I want to call out is deduplicating data. It's really important that we look at deduplicating data, because DATANUCLEUS is very liberal about making copies of data and data in the database and objects in the JVM. So there's a lot of waste, which we'll go through in the following slides and actually start to quantify for you. So given these set of lessons that we learned by examining the existing schema, let's see what happens when we apply them. So this table this table shows some of our findings. Let's focus on the first 3 rows of this table. For this analysis, we used a schema that we pulled from one of our medium-sized metastores, which contained 3.3 million partitions and just slightly over 12,000 tables. So looking at the first 3 rows of this table, we see some information about SDS and SERDES. These are 2 tables that exist in the current schema. The SDS table stores storage descriptor object data, and the SERDES table stores SERDE object data. So each table has 1 record for each table and partition that the Metastore manages. Hence, we have 3.3 million records in each of these two tables, the SDS and the SERDES table. So the problem that we find here with the SDS table is that there are 2 problematic columns. One is a location field, which defines the location on the HDFS where this particular object can be found. The second column is a pointer or a reference to the column set that is associated with that particular table or partition. Unfortunately, the existence of these 2 columns in the SDS table make every row unique. So if we were able to take these 2 columns out and put them in a more appropriate table, then we could go and deduplicate all the remaining records, and what we would find is that this table really only has 6 distinct records. So we go from 3.3 million records down to 6. The SERDES table is actually even more easy to work with, because there are no columns that are disruptive like that. We can just deduplicate the data, and we go from 3.3 million records down to 11 distinct records. So at this point, it's sort of hard to even justify why we need 2 separate tables just to store 17 distinct records. So when we go and design our new table in the new schema, we'll just merge these together, and we'll populate it with a materialized join of these 2 values. And that will result in a grand total of 15 distinct records. So just think about this. We started off with 2 tables that we had to do a join against, each containing 3.3 million records. We do a little bit of redesign. We deduplicate the data, and we're down to a single table that has 15 records. So the other thing that we get from this is sort of an understanding about what this data means. We can sort of infer that the number of distinct storage descriptor SERDE combinations is really sort of limited, especially after your Metastore has run for a while and it's reached a sort of a stable state. So we can use this information when we're actually implementing the OracleStore and just pre-cache this information on initialization when we initialize that object. So we'll just read that in from memory, and the only time we ever have to go back to check the database is if there's a cache miss. So what that means is when we're serving objects such as table objects or partition objects, we don't have to do a join against the SERDES table because we already store it in memory. We just do an in-memory lookup. So that should be a very big savings for us. So that's not a bad start, right? Now let's examine the next table. It's the columns V2 table. So it contains 24.9 million records, which represent column information for all of the tables and partitions that the Metastore manages. Unfortunately, when you look at what's being stored, a lot of it is duplicate information which really contains no value for us. So we can just go ahead and deduplicate all of these records that are in the columns V2 table. And when we do that, we find that we can remove 97% of these records, reducing the total record count from 24.9 million down to around 700,000. So again, that's a great win for us. We can do the exact same types of analysis on the remaining tables, and we find that we get, again, very significant reduction in the amount of data that we're storing. The table params and partition params can be merged together and reduced by 99%. The Surday params can be reduced by 99.7% down to just 20,000 records. So hopefully, looking at these numbers, you sort of get an idea of the kind of waste that is being sort of forced upon us by the underlying schema and the fact that we're, we've agreed to buy into the DATANUCLEUS framework. So with this information, we can go ahead and design sort of hopefully a much more performant schema that reflects what we just found out. And because we're no longer tied to the constraints of DATANUCLEUS, we can go ahead and use some of the native constructs and features that are available to us by interacting with Oracle directly. So the only other thing that I'd like to point out here is that the original schema has a number of indexes that were built on certain tables which were meant to boost performance of certain types of queries. At this point, we've done no optimization of the OracleStore tables. So they're just created, they have primary keys, and that's all they are. So keep that in mind when you look at the performance numbers in the following slides. So writing the code for the OracleStore implementation itself was relatively straightforward. All the code changes were additive. We didn't modify any of the existing code in any significant manner. The only exception to that was adding a number of annotations to the RawStore methods, which helped us identify methods as being either read or write operations. So the reason why we wanted to do this is because we wanted to create a second RawStore implementation which would allow us to T writes and or reads, depending on how it's configured, into both schemas. Finally, we wanted to make sure that while we were writing the new code in the OracleStore, that we did not forget the lessons that we learned from DIRECTSOL. So we wanted to actively use batch queries and optimize those types of operations in a way that DIRECTSOL had done in order to leverage those type of operations. And finally, in order to maintain a very lean footprint, storage footprint, we wanted to make sure that we aggressively deduplicated any new data before it was written to the database. So now we have the following architecture. This is what it was, and this is what we have now. So we've got a new schema, and we've got some new code to work with. Let's throw it into the deep end and see if it sinks or swims. So we started off by running a series of tests. We gathered information from Metastore audit logs, and here you can see sort of the ratio of the operations that are requested or that a typical Metastore would experience. Note that the first column, or the first item in this table, get table, is overwhelmingly dominant. It accounts for more than 50% of all operations that the Metastore is responsible for answering. So we'll come back to this a little bit later. So So we can classify the first three operations as being point lookup operations because they just fetch a single object from the database and return it back to the client. The fourth item here is get partitions by filter. That's a list operation because it returns a list of partitions back to the client. So we started by looking at the point lookup operations. And good news, the performance was at least on par or better than the DATANUCLEUS implementation for the three most common operations. So then we move to list operations. The get partition by filter takes a filter string, which is parsed, and then pushed down into the database in order to apply conditions when generating the list of partitions that it will return to the client. So for this test, we used a table that was partitioned across 6 columns and consisted of 88,000 partitions. So we ran a number of range queries on 4-hour increments and got the following results. So if you look at the rightmost set of bars, that represents 24 hours worth of data. And the size of the result set is 13,000 partitions that were returned to the client. So in this case, we see that DATANUCLEUS took 134 seconds to generate the result set and return it back to the client. We can see also that the DIRECTSOL implementation is by far much better than the DATANUCLEUS implementation, and it does the same amount of work in just 38 seconds. But it's still being constrained by the underlying schema and the DATANUCLEUS framework. So freed of these constraints, OracleStore was able to generate the same result set and return it back to the client in just under 3 seconds. So that's 46 times faster than the DATANUCLEUS implementation and 13 times faster than DIRECTSOL. So we were, of course, very happy about these results. So next, we followed that with a series of tests where we added one more filter condition. This pruned the result sets considerably from 13,000 partitions down to about 400. And OracleStore still performed better than the other 2 implementations. And the same when we added yet another filter condition. So for the next set of tests, we pulled all of the read operations out of the audit logs for one of the Metastore servers for a 24-hour period of time. And again, note that the get table operation here makes up 79% of the requests, or 215,000 requests that the Metastore had to process. Also, one other thing I want to call out is the get partitions method, which actually falls very low on this list and amounts to only 0.1% of the requests, or somewhere around 350 requests. So we'll see that in the next slide. Here, we replayed all of the audit logs against each of the 2 implementations, the DATANUCLEUS DIRECTSOL implementation and the OracleStore, and we found that the DATANUCLEUS DIRECTSOL implementation was able to run through the audit log in about 3 hours, while the OracleStore implementation completed the same amount of work in 42 minutes. So that's about 4 times faster. So here in this chart, we see the performance characteristics of each of the individual operations. Notice the get partitions operation on the far left, which is the operation that DATANUCLEUS and DIRECTSOL struggled with the most. Now remember from the previous slide that this operation accounted for only 0.1% of all requests, yet it dominates in terms of the operational latency. So if this type of operation were requested more, we would potentially have serious problems. With regard to the get partitions operation, OracleStore was able to perform 11 times faster on this operation, and it was able to perform 2.5 times faster on the get table operation. So let's look at some of the other list operations. So we see here that OracleStore performs either slightly faster or as much as 3 times faster, depending on the operation that we're looking at. And continuing down the tail a little bit further, we see the same. The obvious exception here is the get partition with auth operation, for which DATANUCLEUS DIRECTSOL performed better than OracleStore. However, remember that while the original schema has a number of indexes which help speed up these types of queries, OracleStore does not yet have those indexes built in. So, in closing, we have successfully deployed OracleStore to 4 of our clusters, and it's been configured to T writes into both schemas. All read operations are being answered from the OracleStore tables only, and we have a scheduled process that runs once a day, which goes through all of the objects in both of the schemas, does an object-by-object comparison, and validates the data integrity between the 2 schemas. And for anyone who is interested in some of the more gritty details of this implementation or proposal, you can look at Hive 14870, which has sort of a detailed proposal, some of the same numbers that you saw here, and an older reference implementation of OracleStore. And finally, we can talk about some future work. So remember the preponderance of get table requests? A large number of these requests were actually for the same object being requested by the same client. And this is being caused by the middle layer, the core code layer, which is needlessly making repetitive calls to retrieve the same object. So Hive 9453 introduced a mechanism to better be able to handle this. It's a caching mechanism at the RawStore level, which allows us to, on a per query basis, cache objects and just pull them back, as opposed to having to rebuild them from the database every time an operation is encountered. And finally, as I mentioned earlier, we have the thrift layer communication protocol. So the objects that the thrift layer uses are very similar in structure and in nature to the objects that are used by the ORM layer. So these objects, as a result of that relationship, these objects should exhibit the same types of opportunities to be able to optimize and reduce the impact of duplicated data, which should drastically reduce the amount of payload that we're sending back over the wire to the client libraries. So that concludes my talk for today, and I would be happy to try to answer any questions that you might have. Sure.
That after, say, a few hundred partitions, that the trade-off between having the metadata query versus the data optimization for only querying like one of those partitions, it fell off. So if we started hitting thousands, the metadata query would be very slow. You might as well just query more data at that time versus running the metadata query. Is there now like a multiple that we can use in terms of, can we do partitioning in a more granular way now? Like we used to do a few hundred. Does this mean we can escalate the amount of partitioning we can use in our data sets?
So we're getting one comment from back there saying, no, please don't do that. So the performance numbers that we saw seem to be promising. So they seem to hint that we should be able to handle larger numbers of partitions. I don't know that I can give you a thumbs up and go for it. I think we would have to look at it sort of on a case-by-case basis and better identify how many partitions you're actually talking about adding. Yeah.
If I could add to what you said. So the database level, I think Chris has more or less resolved. We still have issues with thrift traffic. So
these tests are just in the Oracle piece, they're not, like, say, end-to-end included, correct?
Not yet.
Not yet.
So the performance tests that I ran were end-to-end from client to the database and then back to the client. Yep.
So what part of this is actually tied to Oracle?
The OracleStore implementation. So the piece that replaces the object store is tied to Oracle.
As in, if I wanted to use Postgres, what is the,
Oh, I see.
what is stopping me from using this your schema on Postgres?
There's nothing stopping you. You would just have to write your own implementation that would work with Postgres specific or MySQL specific SQL, right? So,
No, that was my question. Like, is there
yeah.
any special construct you use in Oracle that is not common in standard?
String functions, which are peculiar to, like they have a peculiar syntax that is used that would, you know, you would have to use the equivalent of whatever Postgre. No, not really. Yeah. So the only thing that would be required would be to take the reference implementation that we use for Oracle, do something similar for, say, Postgres. And because there's a high degree of similarity between Postgres and Oracle, I think that should be relatively straightforward. I think probably we've run out of time, so if you have any other questions, I can answer it after the presentation. Thank you.